Good evening, everyone. Let us begin today's session. This is the week 9 session, live session for economic operations and control of power system NPTEL course. And I'm Gavin Meena. I'm currently a fourth year PhD student in power electronics and power system engineering specialization at Electrical Engineering Department of IIT Bombay. We will follow this same agenda which we have been following. We will start with an overview of week 9 and then we will discuss some questions related to week 9. Let us start with today's session. Just to remind you, this is the deadline for tomorrow's assignment. Assignment 9, the deadline is tomorrow, 25th September, and assignment 10 deadline is October 2nd. I hope all of you are able to access the live recordings. The recordings for live session. All the recordings are available on this YouTube channel and you can visit and watch the videos later. Also, the PPTs which have been used in these live sessions are also available on the Google Drive link. We'll begin with the week 9 overview. Week 9 overview was a continuation. Week 9 was a continuation of power system security, which was discussed in the previous week. Here we will discuss the contingency analysis. And then we move to this optimal power flow. And then finally the state estimation. What's the need for distribution system state estimation? And the principle of operation of traditional state estimators. And the need for hybrid state estimators. We will see why do we need hybrid state estimators. We'll start with the power system security aspect. And for doing this contingency analysis, we use this performance index VOCA. For each index, for each contingency, we can calculate this performance index. So this is the weight, the relative importance, which decides the relative importance among the lines. And you can remove this one. The relative importance of the lines is decided by this Wij, the weight for that line. Ij belongs to this line. The line L is connected between nodes I and J. For that, if the flow the flow on line L after the contingency, if it is more than its maximum power transfer limit or power capability, if it is greater than the maximum limit, then this ratio will be more than 1. Pi, PL, PL new divided by PL max. This will be greater than 1. This performance index will be, it is consisting of 3 components. One corresponds to the line limit violation. So why do we need these performance indices? We want to calculate this because let's say we have 1,000 lines and some, let's say 10,000 lines and 1,000 generators. If you want to see n-1 contingency, so there can be total 11,000 possibilities of n-1. So 1-1 outage. Contingency can occur when any of these lines or any of these generator goes out. So we have to check 11,000 combination. We have to run the OPF for these 11,000 combinations or equations or possibilities. And for each of these contingency, we have to check this. So post outage, what is this performance index? So if one of the line goes out, let's say line 1 outage is go or generator 1 outage. So this is one contingency, this is second contingency. The line, let's say 10 outage. This is third contingency. For each of these, we will calculate the performance index. This is 1, 2, and 3. And then one which is having the maximum value will be used in the selective list. Because solving these 11,000 combination within a very short time is not possible. It will take a lot of time. Computation requirement is very high here. And we want to do this contingency analysis on a real-time basis, almost real-time, because load is changing on a real-time basis. So every time we'll be having different parameters. For that, we have to run OPF each time the system changes. And for that, we want to do very as quick as possible, very fast. We need to reduce this set of contingencies n-1 contingencies. How to select that set? For that, we are using this performance index. For each of these 11,000, we can calculate this performance index. And for those which have a very high performance index, we can choose say some 1,000 or 2,000, whatever. So the highest, the first 1,000, if we arrange these contingencies in when decreasing order of performance index. Then you can select the top, let's say N. N can be anything, 500,000. Top N contingencies which can be used to do the contingency analysis. So now this performance index has three components. So one, and there these three components corresponds to three different violations. The first one corresponds to the violation of the line limit violation. Second, these two corresponds to the voltage limit violation. The first one corresponds to the minimum or the lower limit violation, lower limit voltage violation. Second one corresponds to the maximum voltage the higher limit, upper limit of voltage violation corresponding to the upper limit of the voltage. So line limit violation and voltage limit violation, but lower and upper limit violation. So here same thing we can see here also. Just remove all this first. So this first one is the line is over limit. So PI will be large when any of these three occurs, or at least one of these will occur. All of so these two cannot occur simultaneously on a bus. Either the voltage at the lower limit will be violated, or the upper limit. Either of the two will be violated, either of these. And these two can happen together on a bus. So right limit can be violated and voltage limit violation can happen at any bus. So in that case, this PI will be a large value. So it's the same thing written here. We evaluate the PI, the performance index for each contingency, and the higher the PI, the more severe is the contingency, and that contingency will be higher in the list. So these contingencies are then ranked in decreasing order of performance index that also we have discussed. Now selection criteria for contingencies analysis. Here we want to, so we have two options. Either we take all the contingency and we use the full AC power flow with all the contingencies. That will be most accurate and the most extensive one covering all the contingencies, but it will be relatively slow because solving ACOPF PF is slow and then we are adding all the contingencies. It will be accurate, but it will be slow. We can utilize one fact that power system is designed in such a way that one n minus one contingency, uh, only very few solutions will result in an over voltage or under voltage or overload of line. That's why we can use this design aspect to do our to reduce our contingency set. But reducing the contingency set can result in errors. The first error can be we place too many cases on the short list. If we place, if we add too many cases, then it will result in a very higher runtime that we don't want. And if we have very few cases or we skip cases, then the chances it might happen that the problematic case, the the case which was actually creating a problem, we may miss out that case, and its probability of happening may be quite high, and that and it might happen and occur, it might occur, and the operator doesn't even know about that. So operator is not warned. He only knows when it actually happens. So that contingency goes without any warning. It happens without any warning because we have not included that in the shortlist and it is not analyzed. So that can create problem for the system and we don't want that. So all the critical contingencies we want to include in this shortlist. That's why performance index can help us in doing that. So methods, there are two methods for doing this contingency selection. One is concentric relaxation and second is the bounding. Next we move to the typical, the optimal power flow. So this was first one was the performance index or the contingency selection for criteria for different contingencies. Now we'll see the optimal power flow, which is an important part of this week. The next week will be continuation of our last topic, which is rate estimation. We've already seen in week 2, week 1, week 2, economic dispatch. OPF is an extension of economic dispatch. You will also see one example. For economic dispatch, we are only we are minimizing the cost, generation cost, operational cost of generators subject to one is power balance constraint, which is sum of all generation, output of all the generators is equals to the demand. And second is that all the generators are within their upper and lower bound. This was a simple economic dispatch. It can be with or without losses. So no network is involved here. But the secure and reliable operation of a power system demands that there must be a secure and reliable operation of our system. We require that operational limits for several equipments, for different equipments, are satisfied. And therefore, we want the network to be incorporated within this optimization framework. This transmission line is also one of the equipments, and we want the transmission line, the flow over a transmission corridor or transmission line is below its thermal limit. Otherwise, increased loading or the transmission line can damage the line. The sag can increase and it can even melt. The conductor can melt. So you always want to keep a safe buffer that for any device. For every device, for line we have maximum minimum limit. We want voltage to be within lower and upper bound, which may be 1.05 to 0.95 per unit. We don't want voltage collapse to happen. If we have two buses, bus I and B, and this voltage at ith bus is fixed at 1 angle 0, and this line we are increasing the power drawn at the receiving end, maintaining the sending end voltage. Then what will happen at the receiving, as the power drawn increases, the current to this line will increase. As the current will increase, Ix, the drop, voltage drop will increase. And as the voltage drop increases, this Vj, the receiving end voltage starts dropping. And it can keep on reducing as the power drawn of the line increases. We don't want this to happen. And that's why we want the voltage at each bus to be within this minimum maximum, this band of 5%, between 0.95 to 1.05%, 1.05 per unit. Several other limits, like we have different, we have reactive power sources and things that we have seen. We have tap on-load tap changing transformers. So we want to, their taps also have they have a limited number of taps. So if we have a variable for tap, then that also should be within that its operating range. If there are 16 taps, then that variable corresponding to the tap for the transformer cannot go beyond 16. And it is also a discrete value. Although we use it while modeling, we model it as a continuous variable and we can approximate it to the nearest integer if we have 1 to 16 taps. And while doing OPF, if the solution for one transformer comes out to be 1.01 or 1.78, then we can take it to be 1 and this we can take it to be 2. And then again revise, do the iteration. Finally, if the solution converges, we can get uh, the required number of taps. So if we include these different the operating limits of equipments here in this ED constraints, then the overall problem becomes an OPF problem, optimal powerful problem. You'll see this is a typical structure of the optimal powerful problem. Here we have the objective function, which is f set. There can be different objectives. The most commonly used, which we have been using in economic dispatch and unit commitment, is to minimize the operational cost, total operational cost. So that can be the objective. There can be other objectives as well that we will see. And this objective is subjected to different constraints. These are this is equality constraint, and these are the inequality constraints. And where is z bar is these are state variable. State and control variables. In state variables, we have two variables that we want to, which are out to main output, which we want. The state variables are the V and P and delta, the voltage magnitude plus the voltage magnitude and angle. And then we can have different control variables. So one was the tap of transformer. Is one variable output, reactive power output, the output of these reactive power sources. You'll see these different outputs. Okay. Let me just remove this. Yes. The state variables are these plus voltage magnitude and angle. These are the different control variables which we can control. And the line flows, we want them between F max and minus F max. Load shedding, the FL, we want to be between its maximum and minus maximum, because the flow can be positive as well as negative. Load shedding, so load curtailment is a control variable. We don't want it to be there. We don't want the load to be curtailed. That's why it is one of the objectives can be to minimize the load curtailment, minimize load shedding or load curtailment. Or there can be one we will see it can be a multi-objective optimal power flow where the first objective is to minimize the total operating cost, and second objective can be minimize the load shedding. And the priority, if the priority is not to have load shedding, then we can give a very high weight to this load shedding in comparison to the this first objective, which is the total operating cost. If we assign these weights W1 and W2, and these two are between 0 and 1, then W2 should, if it is much larger than W1, then we can ensure that there will not be any load shedding. So objective optimization problem will be driven towards a solution which gives minimum load shedding. But we don't want frequent interruptions. And this load shedding variable, if we call this as P, let's say PLS, P load shedding. So if we are doing it only for a one-time block, then it should be, we want it to be positive and it should be less than the demand. The load curtailment cannot be more than the demand itself. That is not possible. So that is the upper bound on the load shedding, but we don't even want that a very high value. It should be very high. We can even keep it 0.1 or something like that. That is also possible. That can be done because we actually we don't even want load shedding. But if in certain cases, especially when renewables are there, sometimes it might not be possible to meet the load. We can have some lower bound, a very what we can, the upper bound can be kept as a very small fraction of the demand. The most conservative approach is to keep it as same as the demand for that time block. Then the phase shifter tap position, the phase shifting transformer data position, then the load 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 tap changer transformer, its tap position, and the output of reactive power. These are the control variables. Then we have constraints. We have two types of constraints which we already see here. This is equality, which is the power balance constraint, and inequality, which have this inequality constraint can be limit on these control variables, and same thing is written here, the production limit on generators. This is what we also use in economic dispatch also. This limit on production limit on generators, allowable bus voltage limit VI should be between VI max and VI min. Generator 1.05 and this is 0.95. Similarly, we can have allowable power for limit through each transformer transmission line, and we can also have the limits on these each of these control variables also. And the parameters which are the input which is generally available for carrying out this optimal power flow is are the generator characteristics. It can be linear, it can generally it is quadratic, it can be piecewise linear, it can be cubic, a piecewise quadratic. Then we have generation limits available with us. We have line impedances, we have network topology, and as well as the network security limits. All these things are available to us, and based upon this information, we can carry out the optimal path flow. These are the different types of objectives which are there in optimal power flow. So this is the most widely used, which is also the objective function of for carrying out economic dispatch and unit commitment. Second is the minimization of active power loss. The minimization of loss. We'll see there are two approaches for that also. And third one is the security constrained optimal power flow. We want the system to remain. The system should be able to operate reliably even after a contingency occurs. Even if there is a contingency, a system should be able to operate within its normal operating condition. So that is security concern optimal power. And this can be preventive or corrective. It can be even both. And so you can prevent and so it can be combination of two, because if we do preventive OPF, then the cost of prevention, avoiding any kind of to preventive, it means to allow the system to operate in any kind of n minus one contingency. So it will operate the system in such a way that even if there is any contingency, it will work. And the output, if we'll assume that the contingency will happen, and it will, the output will be such that the contingency is sure to happen. Corrective, on the other hand, will try to take measures when a contingency occurs. If a contingency occurs, then it will take some action to minimize the control required. So this preventive will require a lot of reserves, and it adds to the cost. And relying too much on the corrective OPF, sometimes it might not be even feasible. It might lead to infeasible solutions. The control actions might not be even available to that. So to avoid, so it's a balance between the cost and risk. So it's a trade-off between cost and risk. If we want to minimize the cost, then we have to be ready to face the risk of load shedding. And if we just focus on minimizing the risk, then there might be a problem that a control action is not even available. There are some, so this is one preventive, second corrective. The third is preventive corrective. It uses both. It will try to minimize the cost as well as the risk, both. It will be an iterative procedure. We'll see an example for preventive security constraint OPL. Then last one is the multi-objective OPF. Just a minute. these are the different objectives. Applications of optimal power flow, this we have already, these two we have already discussed. One is preventive dispatch. With the available short-term load forecast, we can do a preventive dispatch. And in case of emergency situations such as line overload, or some outages of even lines in case of some disasters or that size. I mean, generally, when cyclones are there, or heavy, very high speed wind velocity is quite high. In that case, some lines need to be, then in that case, corrective dispatch needs to be done. Planning study is another example where we have to in planning studies also we use the optimal power flow to determine maximum stress the transmission network can withstand. Do we have the adequate transmission capacity to satisfy the future load? Or just this is one thing, we can calculate the transmission line requirement. Second is we can also check uh, the capacity, the generation requirement, the additional generation capacity installation. Additional generation capacity requirement or additional transmission line requirements. All these things we can know. So all these days planning studies also use these power flow constraints, optimal power flow constraints. Then this we already know, we use it in minimization of total cost. There we try to find out the optimal generation and control options for minimum cost and system security. We want to ensure both system security as well as the economic operation of the system. And last one is the economic analysis to determine the LMP, the location margin price. So we will see one example where we have the SCOPF also and LMP. We calculate the location margin pricing. So when we are doing this OPF, LMP is an output of that. We can easily find out the LMP. And these are also used in these power exchanges bid matching. So there we use power flow constraints. We can use OPF constraints to calculate LMP. Next is the challenges in OPF. The problem with OPF is one is the non-linearity and the non-convex nature of the problem because of the non-linear terms like sine and cos, and then we have product of voltages. Then discrete nature of the variables, which are these transformer taps, status of this. If we have switched capacitors, then how many capacitors to be connected in parallel or series, that we need to know to maintain the voltage at a particular bus, or shunt reactors in case of Faraday effect. So all these are when we are dealing with numbers, whether they are number of taps, number of capacitors in the capacitor banks, or the number of reactors in a shunt reactor. All these numbers are integers, and this make the problem combinatorial. And the combinatorial problems are in general difficult to solve. And to make the problem worse, the size of the problem here is quite large. We have thousands of lines and hundreds of control variables. So this makes this problem very computationally challenging. First, the size is very large, and second is non-linearity in the problem, and third one is the discrete nature of variable. It becomes a very large mixed integer non-linear programming, which is in general very difficult to solve. We have these different solution methods. These three we have extensively used: economic dispatch, lambda iteration, and gradient method. These two are they have very slow convergence rate, so they are not used. In Newton's method, including these three methods, they have difficulty in handling inequality constraints. Fourth one is LP. This also we cannot use if we want to use the exact system details. Then LP cannot be used because the actual system is non-linear, non-convex. The LP, when we are using LP, then we need to make a linear approximation of the system. Either we go for DC power flow constraints, optimal power flow constraints, or we use a linearized AC power flow. Constraint, linearized AC power flow. So here then also it will become a mixed integer linear programming. The last one is the interior point method. Here it can be used for linear as well as non-linear. So these two are the most widely used methods, and this is the state of art, the interior point method. Let us see these four different objective functions one by one. The first one is the minimization of total fuel cost. Here the cost function, it can be quadratic. Quadratic we have seen. We have used this type of quadratic cost curve. And we have also seen how to piecewise linearize this quadratic cost function. We can take number of line segments here. And we can linearize the curve in between these points. Then it can be cubic as well as piecewise quadratic. We can linearize the function between 2 points either by a line or by a quadratic curve. Then the objective function here is to minimize the total fuel cost. Is sum of cost, generation cost of all the generators. And we have these different constraints. So these two are the equality constraints, G of Z bar, the real power, and the active power balance. Real power balance and the active power balance constraints. Then here we have limits on these are inequality constraints, limits on the control variables. State variables, the limit on voltage, P and Q, and limit on current also. The second one is the minimization of active power loss. In minimization of active power loss, the generator output, the generator real power output of P is not taken as a control variable. Here you see P is a control variable and it is between its limit, minimum and maximum limit. But here the P is not taken as a control variable. It is assumed to be fixed by once doing the economic dispatch or the solving the cost minimization problem. The generation for all the generators except for the slack bus, except the generators at the slack bus, their output is considered as fixed. So these are the assumptions. Here is economic, we do this economic dispatch or cost minimization. We solve it beforehand and the output of the generator except the generator at slack bus are fixed. And then the transformer tap ratios are they are optimized to minimize the total loss. These are considered as continuous variables and then they are adjusted to the nearest step position in each iteration. And these are the different control variables used in minimizing active power loss problems. One is the generator bus voltage magnitude, then transformer tap ratios, output of reactive power sources or sinks, and the phase shifter angles and all. Or these are the two approaches. First one is the slack variable approach. Here we here we minimize the total system loss. So we minimize the output of the generators connected to the slack bus because we can see the because we assume that the losses are supplied by the slack bus. So if we minimize the output of this slack bus, output of the generators connected to slack bus, then we will minimize the total system loss. So this is the advantage of this approach that we minimize the aggregate system loss. But if we want to minimize loss in a particular area, that we cannot do here. So for that, the second approach is there where we sum the losses of all the individual lines, the summation of losses on the individual lines. So here we consider the losses of all the lines and we sum them up. And we can assign weightage to different lines. The area where we want the loss to be less, we can assign more weightage to that area. And here the objective function is quadratic if we represent the voltage in the rectangular coordinates. Here you can see this will be the objective function for the second case for approach 2. Summation of losses of individual lines. So this is the approach 2. Here this PL is the loss of line, power loss in line L, which is equals to I square into I square into R or I square by GL, conductance of that line. Both in polar coordinate, it will be like this. It will be VI square plus VJ square minus 2vi vj cos of delta I minus delta j into dl. And here it is ei minus ej square plus fi minus fj square into gl. And the constraints will be same here. All the operational limits will be there. And additional constraint will be there for the tap, transformer taps. Security constraint OPF. This is the third one. Here the objective function is, here the objective of the security constraint optimization is to create the contingency constraint so that the resulting OPF solution will not have any overloads in any line when any line outage occurs. This will create a solution such that there is no overload. Here you will see one example. Here the approach is that we adjust the control variables in such a way that the security margins are maintained. One of the control variable is the output, the real power output of the generators. If a line, let's say we have this 3-bus system, and we have generators here and load is here. Initially, these 3 lines were there and these 2 generators were supplying the demand here. 150 megawatt, 100 megawatt by this generator, and 50 by this generator, and all the line flows are within the limit. But if I remove one of the lines, let's say one line is under outage, this line is under outage, and the load is now to be served by this generator, 150 megawatt entire load is being served by this generator. And it says the generator has a capacity of 150 megawatt. So now this line, let's say its capacity was only 100, it becomes 150 megawatt. So the line flow here is violating its capacity. We don't want such a situation. In this case, it might not be possible to supply the limit, supply the demand without violating the security margins, and the load need to be curtailed here. The 50 megawatt of load will be curtailed here because it is a very simple, a small network with no redundancy as such. So instead of this, the network, if the network could have been like this, and one of these line goes out, then we can still supply the load. The entire 150 megawatt load can be possible, can be supplied. But in this case, what will happen? The flow over these line, these will be adjusted. These will be rerouted. In that case, the P, the control variable P and F, the line for these two will change here to maintain the security margins. So it is desired to ensure the security of the system even after a contingency occurs. And the most common method to include security constraints into the OPF is to use the linear sensitivity factors. Power transfer distribution factor and load outage distribution factor. These two are sensitivity factor. It will change us how much changes in a particular line flow or a change in injection or for a transaction between bus I and J. Or generation shift factor, you can say. If what is the change in line flow for a change in injection at bus I. This will be these are sensitivity factors. We can use them to do the security constant OPL. For each of the control variables, we can see how they will change. This is an example here. If we have tap, we consider the transformer taps, then at each bus we have the power, the real power injection, which is a function of voltage theta as well as T, the tap, transformer tap. And if U is the control variable, U are the control variables, generator output or flows, and X is the state variables, voltage, magnitude, and angle. That is the transmission dependent variables such as flow, the MVA flows. Now we want to find out the sensitivity of these MVA flows with respect to each of these control variables U. With respect to each of these state variable X. Now H is a function of U and X, control variable as well as the state variable. We can write then delta H will be equals to df by d x1, df x1 by dx2, so 1 upon df x1 by dxn. This is with respect to the state variable. Similarly, we can write it with respect to the control variable, each of the control variables. So finally, we can write delta Hs in the form of matrix. These are the Jacobian matrix. So how the transmission dependent variable change with respect to the change in state variable and with respect to the change in the control variable. And we also know that the change in control variable also results a change in the state variable. And from here we can substitute delta x is equals to jhx inverse jhu into delta u. And we can substitute it here. We'll get So we get this one. So let us see this example for the security constraint. Here we have a 3-bus system and we have 3 generators. We have generator on each of the buses and as well as load on each of the buses, EG1, 2 and 3. And each of these generators, they have a quadratic cost curve, which is given here in this table. And they also have a minimum maximum limit. G3, it has a minimum limit of 20, 50 and 200. And this is 100 and 400. And this PG1 is 150 and 60. If we perform it, this has been no problem. Yes, so this is the first one. Here, if we simply do the economic dispatch, we're not considering any line flow limit. We simply do the economic dispatch and we can use any of the methods. Here we are not considering the losses. We are only doing the DC without loss, economic dispatch without loss. You can use lambda iteration or Lagrange relaxation, whatever you can. The Newton's method can also be used. Gradient search, anything can be used. And if you use that, we find out that this here we have 2 lines. Here you see there is a redundancy between bus 1 and bus 2. We have 2 lines, each of them with a capacity of 75 megawatts. And this other 2 lines have no, they have very high capacity. Only this line has a capacity of 75 megawatts. And here you see that if we carry out the economic dispatch only, then there is an overload by 5.46%. The line 1 and this line 1, 2, both the lines, they are overloaded. The capacity is 75 megawatt, but the actual flow is 79.095 megawatts. And in this case, we saw that one of the application of OPF is to do economic analysis, and we can find out the LMP, location marginal pricing. Here you can see the output of this problem is also LMP because because this is simple economic dispatch, network is not considered here. That is why LMP will come out to be same. LMP will be same here for each of the network because there is no generator. It is as if we say that all these 3 generators are connected to, they are supplying the load on this bus 1, let's say. All the generators are connected directly to the load. There is no network. In that case, the incremental cost will be same. or there will be only one incremental cost. So that's why you see LMP here is 9.1483 for all the buses. Now if we do the DC OPF, we include the network constraint here. So in that case, what will happen? Because without considering the network, the line flow limits, these two lines were getting overloaded because of generation X. This power flow from 1 to 2, bus 1 to 2. Now if we limit this line flow, then if we include the line flow limit, then it will become 75 and 75 here, and the amount of generation here will be reduced. And we see it was 93.17, now it has become 82.72. There is a decrease in the generation, and as a result, this line flow, because the generation here is reducing, the line flow here also is reduced, because this is reduced to supply the demand, and this is also reduced, and this is also reduced. Because this line flow is reduced, so we can easily, this generator can reduce its generation, and it was already supplying, because on, if you see, this is reduced, so this line flow is reduced. The demand here is 100 megawatt. This generator is supplying more than 100 megawatt. If this is reduced, output of the generation will reduce. The generator will reduce, and because this is reducing, the net outflow from this bus will reduce. You can see it was 57, now it has reduced. And because this has reduced, all the inflow to bus 2 have reduced. Therefore, the generator P2 has to increase. So here the generator 2 increases. Now because of this congestion here, because of this line 1 and 2, both these lines between buses 1 and 2 getting, means hitting their limits, the LMP will change now. Because for any additional increment here at this node, if we want to supply increased demand, let's say by 201 megawatt here, then it can be easily supplied by the generator at this bus. And here, none of the generators are on their limit, we can say. None of them have hit their limits. So once, as soon as there is a contingency or constraint, there is a limit which is hit. Here you can see as there is this we can say it is unconstrained optimization. There is no line flow limit here. This is constrained. Now in this case, the line has hit its limits. Therefore, the location margin price at each bus differs. They will change here. And they see the cost, increment in cost. There is an increase in the overall cost by 40 cents. Okay. Still here only from case 1 to case 2. We have only introduced the network limit, network constraint, only the line flow limit. Now let us further complicate it. Now we will add one more. We will make it security constraint. We will say that we want the system to work even if there is a contingency, which is this. If this one of the two parallel lines goes out, then also we want the system to run perfectly. So in preventive SCOPF, the output of these generators will be such that it will take care of the contingency. Even if contingency occur, the preventive SCOPF will give the outputs corresponding to the outage line. Okay, here we see in both the output here, solution under contingency and preventive SCOPF. Their cost will be same because preventive SCOPF will schedule the generator such that it takes care of the contingency. It will schedule it such a way that the solution is corresponding, the generation is corresponding to the contingency. Even if there is contingency, the generation output will not change, the flow will change themselves in such a way that still the line flow limits are respected, satisfied. Here we can see, but in this case, because line flow limits have changed and this line will hit its limit, the LMP will change here. So you can say LMP. This was LMP for the base case plus LMP for the contingency plus LMP for what do you say? Congestion. Sorry. So LMP will have these three components. If there is no congestion, then these two will be same. It will same as the base case. If there is congestion, then it will be the sum of these two. If there is contingency as well as congestion, then all the three will be included, which is in this, which is happening in this case. Now here we see, here there is no congestion. Therefore, LMP is same at all the three buses, but it is different from the base case. The LMP in this case, preventive SCOPF is LMP for the base case, unconstrained case plus LMP for plus some terms, or we can call it as LMP, component of LMP corresponding to the contingency. Sorry. Yes, we can say contingency. Okay. Here there is no congestion here. So here, no congestion. We'll have same LMP at all the three buses. We can see generation is 275 and the flow is well below 75 megawatt. This is 400 or this is 175. Now, even if there is a contingency, preventive means that even if there is a contingency, this schedule will not change. And we can easily see that I was saying that if you want to do a preventive SCOPF, then it increases the cost because we are moving away from the optimal generation schedule. Here we see the cost was 8194.40. Here, to make the system more reliable, we have to bear the cost. It is higher. Even if there is a contingency, the schedule will not change, but the flows will readjust themselves, and as a result of that, the LMP also, the location margin pricing also changes. And here the LMP will become LMP base plus LMP contingency plus LMP congestion. All these three together will form LMP here. We can see here. Same schedule, but change in line flows as well as change in LMPs. Here, because of congestion on this line, because this line has hit its limit, the LMP changes here. Now, moving before that lesson, so this was the part of security constraint OPF. Now we'll see that. Let me add let me just add some blank pages. Insert. Okay, one is sufficient. I will erase it. Last one was multi-objective. Multi-objective OPF. Here we can have more than two or more than two objectives which needs to be satisfied simultaneously. Two objectives which need to be satisfied simultaneously. Yes, Mahesh was saying something. Or you have typed, you have written it. Yes, correct. That is correct. So we have two conflicting objectives here. So one was minimizing cost plus minimizing the load shedding. If you want to minimize the load shed, then cost will increase. And if you want to minimize the cost, load shedding might increase because the cost of load shedding is quite high. We keep it quite high because we don't want load shedding to happen. So that is why this is main object. There can be more than two objectives here. You can have multiple objectives. So let's say this is our objective function. We want to minimize that, and it can be omega 1 f1 plus omega 2 f2 so on up to some omega n fn. And these omega are the weights corresponding to each of these. The one we want to be prioritized, we give it a higher weight. Okay, now we'll move to the state estimation part here. Traditionally, we were doing state estimation on the transmission system level, which was done based upon the measurements from SCADA. We produce SCADA measurements. This was a traditional, and it resulted in a non-linear state estimator. Because we would get P and Q and voltage magnitude measurements from SCADA. And then we had equations for this P and Q nonlinear equations. Now we have, you can say, modern state estimators. They use PMU measurements. And they can give us a wide variety of outputs. So they can give 24 measurements at a rate of 24 samples per cycle. And the main advantage here is that the measurements are time stamped. It's from the signal from the GPS signal. So here we directly get the V and theta measurement. We also get F and Rokoff, the rate of change of frequency, df by dt. And so this here the SCADA measurement is, we get the measurement is quite, sampling rate is quite small as compared to PMU. PMU samples the rate at a very higher rate. So we can directly get the voltage and angle information, frequency, and df by dt. So this has changed the things. Now even this has made the state estimator now linear. We can use a linear state estimator instead of a non-linear one. Yeah, this was a major breakthrough, and because of using linear, it becomes quite fast. Since the data which we are receiving is also coming at a very fast rate, we need to process it very fast, and because of the LP framework, we are able to achieve that faster processing of the data. Now, the transmission system now we are considering, but another thing here is now we are also concerned about the distribution system, state estimation. Traditionally, we were not talking much about distribution system state estimation because the demand pattern was almost, it was, we were able to predict it with a quite high accuracy because demand was not that uncertain. Yes, it was uncertain, but not that much. But now, because of so many components, so many changes in the power system, because it's grid becoming smart, the demand is becoming uncertain. And there are several sources of uncertainty in demand nowadays because of the distributed generation, electric vehicles. Now they are also parting in demand response, demand side management. We also have behind the meter battery systems. We have peer-to-peer trading systems. All these things are making the demand very uncertain, and it is difficult to predict the demand. That is why it is becoming more challenging now. And to operate the system with such a high uncertainty, we need to estimate the state variables for distribution system. However, the penetration of smart meters, for doing the state estimation, we need to have measurement redundancy, or we call enough observability. So with the given measurements, I should be able to know the states. If number of measurements are less than number of states, the system cannot be observable. We cannot know the states. So we need to have enough number of measurements redundant, not just because of observability, because some data can be a bad measurement, bad data. Because of communication, so the data is coming from through a communication channel, and there can be several errors in that data measure in that measurement. There can be different. There are several sources of noise in the communication channel. Communication channel. And now, because of increasing IoT penetration, the system is also prone to cyber attacks, and that can also make the data bad. And so we need redundant measurements to identify, to remove those bad data and use the good data for the state estimator to get a better picture of the existing system. Now, why do we need this distribution state estimator? As we already discussed, the penetration of distribution generator, electric vehicles, demand response also we have discussed. A storage device also we have discussed. Distribution management system is required for all these things. So all these things we have discussed. And features of distribution system. How this distribution system state estimator will be different from transmission system. And one thing is the differences arise from the inherent differences between the transmission and distribution system. The distribution system is inherently, it is unbalanced. There are unsymmetrical and single phase loads. Single phase distribution lines. We have untransposed lines. And then we have single phase DCs also. And because of all this, we need to do a full three-phase state estimating. We need a full three-phase state estimator. So this is one thing. We need to do a full three-phase estimation because of this unbalanced in presence of single phase equipments. The next thing is the topology. Transmission system is meshed, or a distribution system is mostly radial and very weakly meshed. Then we have R by X ratio is quite low here, R by X ratio is quite high, and which impacts the convergence rate if we use the conventional uh, power flow methods which we use for transmission system. Here capacitances are high as compared, here capacitance is low and hence neglected for distribution system. And the number of buses here is very large number of buses here. And now because of all these things, it becomes quite challenging. And because we don't have enough measurements, we need to go for pseudo measurements or synthetic measurements. And because they are not accurate, their weights which we assign them is low. And this affects the performance of the state estimator because of the large uncertainty associated with these pseudo measurements. The lack of redundancy and uncertainty in network model heavily affect the accuracy of this state estimator. Now we have different functions of state estimator. The first block of any state estimator is the topology processor. Based upon the status of circuit breakers, we first of all get to know the topology of the network, the existing topology that needs to be obtained first. And then we do the, once we know the network or a particular timestamp, then we do the observability analysis. Are the measurements enough? If not, then we add pseudo measurements. Otherwise, state estimation cannot work. We add the pseudo measurements and then we do the bad data processing. This will be going in loop. Bad data. After removing the bad data, again we need to check whether it is observable or not. The removal of bad data is done. Then parameter estimation, line parameter estimation. And finally, last block is the state estimation. All these 5 blocks are required for entire state estimation. The state estimation problem is solved as the maximum likelihood estimation problem. Or we also call it as least squares problem. And the solution for least square is if we have y is equals to ax plus b, it will be A transpose A inverse A transpose B. Here error is y minus x plus b. We want to minimize this. So we want to minimize this will be the solution. And we will see one problem for this. So it is solved as a linear, it is solved as a least square problem. In the traditional transmission system, state estimation is a non-linear one. Non-linear, so it is a non-linear least square problem, and which is derived from the maximum likelihood estimator. And here we assign different weights. Wi with W is the weights for each of the measurement. The measurement which have larger variance, they have a lower weight because their sigma is high. Sigma is the standard deviation here. The measurements that have higher variance are assigned less weight because we have less confidence in measurements having larger variance. The objective here is I is equals to 1 to m minimize Zi minus mu I by sigma I. We want to minimize this where Zi is equals to plus ei. This is the error. This is called as the weighted least square state estimation. Z is equals to hx plus e. Then here we assume that expectation of error is 0. We don't want error in measurement. We want this to be equal. The second thing that the expectation is ei is 0. That is independence. The two measurements are not independent on each other. And as a result of this, the covariance matrix becomes a diagonal matrix here. Sigma square, sigma n square. This becomes the covariance matrix represented by R. Because it is expectation of ei into ei. And ei is Zi minus mu I. What is expectation of Zi minus mu I square? Which is sigma I square. And because it is nonlinear, we need to find out the Jacobian and Hessian matrix. And the gain matrix G becomes the Hessian matrix. Which is the H transpose R inverse H. And finally, the update for each iteration becomes xk plus 1 is equals to xk plus g of xk inverse H transpose R inverse Z minus Hx. And we never do this inverse x because for a large system, taking inverse is very computational. For large system, inverse is never done. We solve this using the decomposition techniques, the LU or Cholesky decomposition. Or SVD or QR. All these things can be used. And this we have been doing with SCADA. Since SCADA measurements are available, the state estimator become nonlinear. And it has a drawbacks because the refresh rate is quite slow. The rate is around have samples. We get a sample every 2 to 5 seconds. And the state estimator will give output every 1 to 5 minutes. The refresh rate for SCADA is 2 to 5 seconds. And state estimator takes 1 to 5 minutes. So that is also it is taking quite a time. More than much state estimator is taking time which is much more than the refresh rate of SCADA. It is very difficult to obtain the voltage phase angle in real time from these dispersed location by using conventional measurement and state estimator. Therefore, the real-time visualization is not possible by using SCADA. And because of all these problems, this PMU was brought in, which provide measurement at sub-second rate. We have 50 to 60 times per second. So, and they also provide direct measurement of the phase angle, which was not possible with SCADA. Now PMU can be integrated into state estimator, and that also make the state estimator linear. And now we have PMU only at substation of 400 and above, 400 kV and above. Below that we don't have the PMUs. Below that we still have SCADA. Now if we want to, we have to integrate these two, measurement from SCADA as well as PMU. So it becomes a hybrid state estimator. We have measurements from two different sources. One is from SCADA, one is from PMU. PMU, which is giving the data at a very fast rate, and SCADA is giving the data at a very slower rate. So there is a difference between the time scale. And we still want to use these two together to get the better uh, state of the system. So using the hybrid state estimator can help in improving the accuracy of state estimator. Also, it will increase the observability because now we have more number of measurements from SCADA. And And because there are more redundant measurement, bad data detection handling also becomes easier, as we have different sources of error in state estimation. One is modeling error, data error, and transducer and sampling error. All these things also we discussed. Now we will move to the questions. First question is that SCADA measurements can provide direct measurement of phase angles. Is it true or false? Okay. Yes, Mahesh is saying it is true, but that's not correct. It is false. SCADA cannot provide a direct measurement of phase angle. SCADA provides us PQ and voltage magnitude only. But PMU can provide us the data for voltage magnitude and angle directly. The second is the calculating the inverse of gain matrix. Is easier if direct inverse is taken rather than using numerical methods. This also we have discussed that for taking direct inverse is not at all recommended. It is to be avoided always. We use different decomposition techniques for doing this, for solving these equations. Because of computation region, we want to avoid this direct inversion at any cost. And we want to also exploit the sparsity, the sparse nature of G matrix. And third is expectation of measurement errors is 0. So is this correct? Yes, you're right. So we have seen error is equals to Zi minus mu I, right? Expectation of Vi is expectation of Zi minus expectation of mu I. Now expectation of Zi is mu I. An expectation of constant mu I is a constant. So expectation of mu I is mu I. It is mu I minus mu I, which is 0. Because we are saying this measurement is a following a normal distribution with mean mu I and variance sigma. So this is true. Oh yeah, we were talking about this question. Here we have a 2D plot. We have 3 points. 2, 1, and it's a curve fitting problem. We have to fit a curve. This is y. So this is ax plus b line. This is x. And these are different points, and we want to fit this line to these points. So error here is Z measurement minus so this is X value and this is these are our measurements Y cap. So Zi minus A X1 plus B1. We've already seen the E is written as Z minus HX. E is Z minus HS. And H is here. What is H? Here is Ax plus B is equals to Hx. So we can write it as like this. X1, X2, X3, 1, 1, 1. And this becomes A, B. This becomes HS. The H, this is the H matrix. And now the solution is H transpose H inverse, H transpose into S into Z. This will be the solution. Here, what is H? H here is 1, 1.5, 3.5. Sorry, these are X and Y. This is X and this is Y now. H is 2, 2.5, and 4. This is 1, 1, 1. And Z is here 1, 1.5, and 3.5. So you have to calculate first H transpose H. So you can easily find out it. Then after finding out H transpose H, you can take the inverse and multiply it by H transpose and Z. Now next one is to calculate the expected value of X. The expected value of X will be Fi Xi divided by Fi. So that will be something like 6.91 something. We can multiply 1 into X is this and Fi's are these values. So you can calculate easily. It will be 2 into 1 plus 3 into 2 plus 10 into 3, so on. Last 12 will be 5, 12 into 5 into 12 divided by all these things. 1, 2 plus 3 plus 10 plus so on up to 12. And you will get this 6.9 something. If the mu x is 30 and sigma x is in, what is the probability that x lies between 24 and 39? You can use this. You can first normalize it. 24 minus mu x by sigma, you will get this x minus 30 by 30. Now this becomes z. It should be between minus 2 and 3. This is 3. And this is, we can write it like this, probability of z minus 2 to 2 and then 2 to 3. And this can be written as this. And this is the CDF. CDF, we can calculate probability of z less than 3, z less than 2. And sum them, you will get this 0.956. Less weightage is assigned to pseudo measurement. Yeah, that is true. So all the questions are. Thank you for joining today's session. We will meet next Tuesday for the week 12 session.